Okay, so hello and welcome. Today we're going to talk a little bit about angular momentum. Now, momentum's something you should have come across already, but usually in the case of things travelling in a straight line. Hopefully you remember from your classes that momentum is something that has both a direction and a magnitude, so a size effectively. And just like linear momentum, which is in a straight line, we can also have momentum associated with spinning objects. Now it's a bit more complicated because if you're dealing with a spinning object, then it's perpetually in motion, of course an ideal case. So what we do is we decide that we're determining the direction as along the axis. So you can remember this as a right hand rule. So if you curve your right hand like a thumbs up, the fingers point in the direction of rotation and your thumb points in the direction of the vector. So that's all well and good, nice stuff. But what does that mean? Well, I've got a demonstration here. So this looks a little bit like it might be levitating or doing something rather strange, but all it is a necessary consequence of the conservation of angular momentum. So just like linear momentum, angular momentum is conserved. In this case, we have our angular momentum travelling along the axis in that direction, and then when I hold it from this string here, the wheel wants to rotate downwards like that. So we have a second rotation, in this case that direction, another angular momentum vector pointing in that direction. And so as a result of this, the net motion produces that precession and stops it from falling down because it wants to conserve that angular momentum. So that is what we're seeing here. Okay, so today again we're talking a little bit more about angular momentum. This is the rotational equivalent to linear momentum, which you should be very familiar with, which is just P equals mv, so momentum is mass times velocity. Now just like linear momentum, angular momentum is also conserved. So if I spin up this rather heavy lead wheel, and I sit down on this very free spinning chair, if I turn it, we end up with a resultant vector that forces me to rotate. And I can use this to control my angular momentum or my angular velocity very accurately. Now, as discussed earlier, angular momentum is given by our right hand rule. So we've got our wheel rotating in this direction, which means that our vector is pointing off in that direction. When I turn it, I change the direction of that vector. And to change the direction of a vector, you have to have a force exerted on it, and that resultant force is what pushes me around in a circle. And by changing the direction of the angular momentum vector, I can change exactly which direction that resultant vector points in, and use that to control my own rotation. Now this is a nice demonstration, but it's also how satellites adjust their attitude, which is not the attitude that you tend to have at school that your teachers complain about. This is the angle at which the satellite is pointing. You could do this with rockets, be very inefficient, but if you have 2 or 3, in fact, very heavy wheels, you can spin them up and use that to change the direction of satellites pointing using just electricity, which is very efficient and much more interesting in terms of physics than just shooting a little rocket out. Okay, so we've been talking a little bit about angular momentum, and we've looked at how it's conserved and what happens when you move the direction of it. What we're going to do today is look at the components of angular momentum. Now what we have is the angular velocity, which is the rotational equivalent to linear velocity, so the speed in a straight line, if you want a very simplified, slightly less accurate term. And we also have the moment of inertia, which is the rotational equivalent to mass. Now the moment of inertia is a lot more complicated. It depends exactly on what shape you've got and how uniform it is, whether it's a solid body, whether it's a hoop. But for the purpose of this video, we can just consider that it takes into account the mass of the system and the radius of the system. Now, as we talked before, momentum is conserved. So what's going to happen when I start off with a nice wide cylinder, or approximating a cylinder, and then bring it inwards. So the radius is getting smaller, which means our moment of inertia is getting smaller, which means as a consequence, my angular velocity increases. And if I do the opposite and go out, hopefully you can see me slowing down. So just like linear momentum being conserved, this is angular momentum being conserved simply through changing the radius of the system and the distance from the center of the system of the mass, which in this case is in these dumbbells.